Okay, can I start?
Yes.
Okay. So, I was telling you that first of all I will give you some preliminaries about our previous work on this topic, the axons. Then I will tell something about general about this boson method or boson transformation method in quantum field theory, and then we'll see how these two things will join each other. That's so. Okay, yeah, I think it's right. First of all, the point was that Bekenstein bound on entropy seems to imply a couple of things, at least led to a couple of considerations. One is that the Hilbert space, or quantum theory, it should be locally finite dimensional. That was argued by Carroll, seeing that I mentioned a bit before. And then it was also argued that such a finite number of degrees of freedom, which are described in this finite dimensional Hilbert space, should count for all kinds of degrees of freedom. So both matter, but also geometric modes. No, because we are looking at quantum gravity. That's the idea. And so, but at this level, you should not have a distinction between matter and geometry modes, and these fundamental building blocks, let's say, were called axons. So this was done in this work by Acquaviva, Yor and Scholz. Then we reversed the logic from that work, and we say, okay, let's start from in the opposite way. We start from the axon point of view. And so we said, okay, a local finite system, it means you have just a finite number of available quantum states, and then we assume that such fundamental building blocks are fermions, as also was said by someone before. And then from this we describe black hole evaporation in this way. We assume that inside a black hole you have only three axons, and when they interact you have black hole evaporation, and they form the matter and the space-time outside the black hole, because when black hole reduces you have more space-time outside in a roughly way, and you have formation of Hawking radiation. That was the basic idea. And the model was proposed in order to describe black hole environment state. In this work was this one. We used the second quantized language, and we called the environment modes the axon which interacted to form the environment with A, and the B modes were the black hole modes. And after that we computed the Bekenstein-Hawking and the entanglement entropy, and we figured out that Bekenstein bound could be a consequence of the fermionic nature of such fundamental building block. So, but in this paper we didn't explain the mechanism. We did a division, but it is no way at this basic level to a division between A and B modes. This was quite artificial and was done for sake of description, sake of simplicity. But how to describe the way these modes interact in order to form, to have an emergent space, in fact, and emergent quantum matter. And a suggestion to solve this problem comes from condensed matter physics. It's known since a long time, for example this work by Katanev, Volvic, but also Kleinert and others, that an effective description of elasticity theory of material of a crystal with defects, for example, can be given in terms of a Riemann-Cartan geometry. Okay, and so you have oh sorry, maybe I meant that. No. Okay, that's one point. You have, in fact, there were proposed models as a word crystal model by Klein. So these, based on similar ideas, there were also proposed these analog system of gravity, for example, in Dirac materials like graphene. Alfredo Jorge talked about this the first day, and Pablo Pais will do after the coffee break, so follow his talk. I strongly recommend. And so the other point, the other piece of the puzzle we missed is the so-called boson transformation method, which had Umezawa and collaborators in the 70s to show how classical elasticity theory and classical description of topological defects emerge after a basic quantum field theory of the molecules of the crystal. So you have a dynamical emergence of the classical theory from the underlying quantum field theory with this method. We say, maybe we could try to combine these two things. It could work. And so now I try to tell you some basic facts about the boson transformation method, just in brief. The basic ingredient is the so-called dynamical map. What is the dynamical map? Let's start with an interacting quantum field equation where lambda is a differential operator. And we can rewrite in this form, which we call the Young-Feldman equation, okay, when you introduce some kind of green function. And psi 0 here is a solution of the homogeneous equation. Okay, now you can think to iteratively solve this equation, at least in principle, and the formal solution is this one. And it's called the dynamical map, in fact. And then we will do a step further here, and we also assume that, let me see what is, yes, sure, inside. We can also assume that a sort of polar decomposition, as you do in the case of the scalar field, for example, when you describe vortices and so on. And we can decompose the psi 0 field in terms of some phi field that, surprise, surprise, will be some Namu-Goldstone boson and some, let's say, radial mode psi. Okay. And then now there is a fundamental theorem of this approach. It's called the boson transformation theorem, which stands the same, the following. If you take this canonical transformation, where fj are C number function, okay, and transform, and these are boson fields. As I told you, it should be Namu-Goldstone boson at the end. So if this transformed field follow the same equation as the non-transformed field, let's say with f equals 0, then you put this into the dynamical map before, and then what you obtain is an entire class of solution of the original dynamical problem. So you don't have just the standard solution with the f equals 0, but changing f, you have an infinite kind of solution of the original field equations. Okay, so that's very powerful. In particular, it's very interesting the case when your function f are non-Fourier transformable. In such case, for example, here where you have some nonce function in some points, you can describe solid or non-topological defects. Okay, so you have quantum solution of quantum field equation with topological defects. Now let's move on. Another ingredient here would be the fact that we start with some symmetry, Lie group symmetry G, and that we have spontaneous symmetry breaking of this symmetry. So some of all the nether charges do not annihilate the vacuum in such case. So in this case, we can now identify these phi safely with the Namu-Goldstone bosons. And we can perform the boson transformation, and it can be shown in the non-abelian case that field psi can be decomposed in this way, where U is a classical gauge matrix which depends on F, okay, and it's a non-regular function, when psi is the regular, let me say, the regular part, where the one where the derivatives commute. Okay, and so after this, from this U, you can define gauge potential and associated non-abelian field strength. But the nice thing is that this U and so these objects come from this boson condensation, boson transformation will describe the condensation of this Nambu-Goldstone boson on vacuum. So are dynamically generated. Okay, so are not put by hand there. And so now, we see, I'm sorry for
the vortex.
The vortex, yeah, exactly, thank you. An example, for example, is the one of a scalar field theory with a U1 symmetry, a spontaneously broken U1 symmetry. In this case, you can write the dynamical map in this general form. And so where key is the Fason, the Nambu-Goldstone boson in this case. And when you perform the boson transformation, so key equals to key plus F, you identify the gauge transformation in this way. Okay, this comes from this result. In particular, for example, when you take F equal to the azimuthal angle in cylindrical coordinates, this describes a straight vortex along the z-axis. Okay, and so you are describing quantum field theory solution in the presence of a vortex. Okay, so that's the very basics idea. Let's try to apply to our case. That's the idea of the schema. Of our paper. As I told you, we started from finite dimensional stuff. And so we are here on the left, on the paper on black hole evaporation. But now, because we don't know basically how to proceed in this way, we use a very wild approximation. We say, okay, these axons are finite but are so many, and so type that we can use approximation in terms of quantum fields. Okay, and so we are basically using quantum field theory of some fermion field for what I've told you. And if our field equation have free symmetry, which is spontaneously broken down to a crystalline group, to a discrete group, in this way, we can show through the boson transformation method that the gauge field, which dynamically emerge from here, are just the field bind and spin connection, and then the relative field strength are the curvature and torsion tensor. And so we recovered the Riemann-Cartan description, at least of space geometry. I was cut a knife and ball.
You necessarily have torsion? You have necessarily torsion?
No. It depends on the type of defects you have. Right. If you have no, let me say, dislocation type defects, you don't have torsion. Okay. So let's start with fermion doublet here, and then this is the algebra of E3. And then let's now, yes. Now let's pose just a problem which was quite hard to solve in this context. It's how many Nambu-Goldstone boson we have to expect. And here we employ this theorem by Watanabe and others, which says that you have redundancy in the counting of Nambu-Goldstone boson just when you have some linear combination, some linear dependence of the nether currents, basically. And this, for example, you have redundancy between typically angular momentum and momentum operator. But the total angular momentum, in the case you have fermion, it's has also a spin part. So if you assume that also the action of the spin operator is non-trivial on vacuum, basically you have 6 independent generators. Okay? And so we can expect up to 6 Nambu-Goldstone boson. This is a highly non-trivial point because in a crystal, typically you don't have such kind of condition, and so you have only 3 Wilson boson, which are the acoustic phonons in a condensed matter crystal usually. And then now we can employ the previous consideration. So we start from our interacting field in terms of the Wilson boson and quasi-particle fermion field. Then we perform the boson transformation, and we get, at least in principle, the solution of the quantum field equation in presence of, for example, of topological defects. If these are yes, sure, I manage.
It doesn't see.
And so,
that's the reason why I'm there.
and so now, okay. Now we can write, you can argue that the unitary, the gauge matrix has this form where y is a function of f. We will see an example in a slide. And then if you take the derivatives, you can find the gauge potential and the field strength, which you can see in all the glory, the curvature and the torsion, spatial curvature and torsion. And these, I remark once more, these now are dynamically generated after the boson condensation in the vacuum, are not put by hand there in the theory, and are classical quantities. And so, for example, we did an example in the case where U is small, like in a linearized context as you do in the work crystal scenario, for example. But we are more fundamental than that because we are making a merged crystal structure with defects. And so the dynamical map in this case should be of this form by symmetry reasoning. And then the y is just x plus u, the one introduced before. And in this case, the very interesting fact is that if you now take the equation for the psi zero field, and you assume that the operator is linear, okay, you naturally, and clearly you have to trace out over the x modes, because these are low energy equation. Then what you get are equation of quantum field, fermion field psi, which couples with torsion and curvature in a natural way. So we made also emerge this quantum field equation of curved background from the basic dynamics. And so basically that's all. I don't repeat everything also because we are late. So thank you for the attention.
Okay, we have time for a few questions.
Before the break? We have time for a few questions. Let's see. Any final question before people running out on the break?
Don't worry. Don't be shy.
Well, maybe now you can share your worries about time.
Yeah, it's true. It's true. As you can see, time basically here. I cannot go here. Yeah, we have no structure in time basically, and if we manage to reformulate everything in the original model, the sigma was just a parameter which counted the average number of exons which interacted. And here we maintain the same interpretation, let me say, but it would be very nice to reformulate everything in a way, in a timeless way. And because it's evident that the structure regarding the time should emerge in a different way, as in many approaches of quantum gravity, as we have seen. So, but let's see, we don't know how to deal with this.
Just a comment about
this point. This is a non-homogeneous boson condensation, as
Yes.
is clear, because you choose a f, which is f of x, with the singularity you are searching for. If you want a vortex, you ask an f. If you want something else, another one. But then it's interesting it could be interesting if you do non-homogeneity boson transformation also with respect to time coordinate.
But the
In
problem...
that case, I mean, things became not so easy, but...
do you know what is the problem? Now I say the real problem here with time is that if you break the time translation symmetry, for example, so you get time crystal basically in the Wilczek you don't have Lamb-Wilson boson.
no, but, okay, but
and so you cannot have, you cannot go on in this way.
sure, but you could introduce some kind of dissipative structure.
Well,
Which,
it can be investigated. We can talk about.
Yeah, sure.
This could be interesting.
Thank you, Luca. Let's thank all the speakers again.